So in this video, we will be solving part 3 of the homework right here, where we have a situation where we're starting from a force balance on a cylindrical control volume with either a pressure drop or vertical elevation. We're going to be doing a pressure drop situation, and we are to show that the fanning friction factor is equal to 16 over the Reynolds number for laminar flow. So again, I said that we will be doing a pressure drop situation. So I have made a diagram of the situation here with our outside cylinder with radius of big R and a flow Q going through there. And then our inside cylinder right here with a radius of little r, and points 1 and 2 will be our points for the pressure, and then it will be a length of delta x right there. So now what we're going to want to do, as the problem states, is perform a force balance for our situation. And the net force will actually equal 0, since although we have a flow rate, Q, right here, it is a constant flow rate, so it's not accelerating, so there's no net force in the situation. So what forces are there, though? So we're going to have the pressure force at 2 and pressure force at 1, so we can write that as P1 minus P2 because of the pressure drop, and they will be acting on the cross-sectional area on these end caps, pi r squared, little r, and then we will have a shear stress acting on the whole outside of the cylinder here, so we can write that as shear stress times the area around the cylinder, which will be 2 pi r times our length, delta x, and that will still equal 0. And then now we can substitute in for our shear stress. It is, for every Newtonian fluid, it is the viscosity times dV over dr, which is the volume and radius. And then everything else will stay the same. And our next goal is going to be to split up this dV and dr onto both sides, since it is a separable differential equation. But first we can see that this r and one of these r's will cancel, and then the pi's will cancel as well. So now if we're trying to get these on the same side, we'll have, or on opposite sides, we'll have dV on this side, and then negative P1 minus P2 R all over, again, the viscosity, or I'm going to put the 2 out front, since that 2 is still here. V2 mu the viscosity and delta x, and then dr. So now what we can do is we can integrate both sides I'm going to give us a little bit more space here. So we can take the integral of both sides. And we'll end up with v equals negative p1 minus p2, and then r squared over 4 mu delta x. And we also can't forget, since we took an indefinite integral, we will have plus c. So now our next goal will be to figure out what this c is. In order to do that, we need to figure out a velocity and a radius that we know. So if we look at what the velocity profile would look like, since this is laminar flow, it would look something like this, where at this outer radius, the velocity will equal 0. So we can plug that in. We can do it up here. So 0 will equal negative p1 minus p2. And then we'll have big R squared, since it is the outer radius. And then 4 mu delta x plus c. So that means that our c will be equal to p1 minus p2 big R squared over 4 mu delta x. And now we will plug this back into here. And with that, we will end up getting that v is equal to p1 minus p2 over 4 mu delta x times little r squared minus big R squared. So I actually made a little mistake here. It'll actually be big R squared minus little r squared because the negative is here. So big R squared minus little r squared, like that. And that will be our velocity of the liquid in this situation. So I'm going to erase all this and put it up here, copy it up here. And what we're going to end up doing is relating this velocity back to our flow rate here, Q. Again, it's P1 minus P2 over 4 mu delta x big R squared minus little r squared. So now, to relate this to the flow, we're going to be using an equation where we know that Q is equal to integral of V dA. So we already have V right here, but we need to figure out what we're going to do for dA. And for that, we are going to look at this cylinder from a top view. So that dA is going to be the circumference over and over and over to get that area. So how we're going to represent that is going to be 2 pi r times dr. As you can see, like circumference over and over and over for every radius that there is. So now we can plug in our v. It'll be q equals slope of the integral p1 minus p2 over 4 mu delta x big R squared minus R squared, and then times our 2 pi R dr. And now what we can do is take our constants out in front of this integral. So our P1 minus P2 and our 2 pi over 4 mu delta x. And then inside our integral, we will have r big R squared minus r to the third dr. And we will be integrating from 0 right here all the way out to big R, because again we just want all those circumferences. So big R right there. So now to evaluate this integral, again our constants will stay the same, but I'm going to simplify this to 2 over 4, which is become 2 in the denominator. So we will have P1 minus P2 still, and then just a pi over 2 mu delta x. And as far as our integral goes, this will be big R squared, little r squared over 2 minus little r to the fourth over 4. Evaluated from 0 to big R. So now when we plug that in, again, constants stay the same. Delta x, we will just have r to the fourth, big R to the fourth over 2 minus big R to the fourth over 4. And then we just find a common denominator here. We will end up with that Q is equal to P1 minus P2 pi over 2 mu delta x, and then times r to the fourth over 4. So now we can actually combine these two in the denominator, this 4 and 2. So it'll end up being, and I'm going to write it up here. We'll have Q equal to P1 minus P2 pi over 2 mu delta x, again 2 times that 4, it'll actually be an 8 here, and then big R to the 4th. So that will be the flow rate in this situation. So I'm going to erase all this. So now what we can do is we are going to want to solve for the pressure drop, P1 minus P2. So we are going to isolate that in this equation. So if we put P1 minus P2 on its own side, it will equal eight mu delta x times q all over pi big R to the 4th. And then now, since our frictional heating equation is in terms of the diameter d, we're going to change this R into a diameter. So radius is just 1/2 diameter. So we will end up with, again, P1 minus P2 will be equal to, will be 128 mu delta x q over d to the 4th pi, like that. And then now what we can do is we're going to want to substitute in for our q, our v times the area, and for that it is just going to be, it'll end up being pi times d squared so P1 minus P2 equal to 128 mu delta x v times pi d squared over d to the 4th pi. And you'll notice that these pi's will cancel, and then the d's will cancel. And we will end up with P1 minus P2 is equal to 128 mu delta x v over d squared. So I did make a little mistake here. Since we use d here, it needs to be over 4. So there will actually be a 4 right here. And then that'll cancel with the 128 and make this 32. So this will actually be our equation for P1 minus P2. 32 viscosity delta x v over d squared. So I'm going to copy that up here. P1 minus P2 equals 32 mu delta x times v all over d squared. And now what we're going to want to do is plug this into Bernoulli's equation. Again, Bernoulli's equation is P2 minus P1 over rho is equal to the negative of the friction factor. That's really bad. Let me redraw this. There. And we will not have the vertical or kinetic energy heads because, again, there's no geometric change between point 1 and 2. And then we have a horizontal cylinder. So that's why we don't have the vertical head as well. So now, as you can see, this is oriented P2 minus P1. So we can actually flip that and make it P1 minus P2. And that will just make this positive. And now what we can do is plug this in and plug in our equation for frictional heating as well. So I'll plug this in first. 32 mu delta x v over d squared rho. And that's going to equal 4 f delta x over d v squared over 2. So now, as you can see, these delta x will cancel. Delta x's, and one of these d's will cancel over here. The 2 and the 32 will become a 16. This v will cancel, and one of those v's. Or excuse me, this 2 will cancel with this 4 first and make this a 2. And then that 2 will cancel with that 32 and make it 16. So again, let me just start to rewrite this. We will have 16 mu over rho v, and that will equal F. So I did miss, there still is a D here, right here, just one of them cancels out. So we will have a D here, and then now this should look relatively familiar because we do know that Reynolds number actually equals Reynolds number equals rho dV over mu. So if we just flip that and say the 1 over Reynolds number is equal to mu over rho dV, and then we can plug that in and say we will get the 16 over Reynolds number is equal to F, our fanning friction for this laminar flow problem.